Hello everyone. Welcome you all to week 5 NPTEL problem solving session for the course Introduction to Group Theory. I am Priyanka Sharma, your PMRF NPTEL teaching assistant for the course. Let's start the session. So these are the topics which were covered in lectures of week 5. First, we will shortly discuss what are the main definitions and results, and then we will come to the problems based on these topics. So in this session, we will discuss what is product of two subgroups, what is center of a group, and normal subgroups, their properties and their examples. The group Q over Z, direct product, in which we will cover both external and internal direct product, and then normalizer and centralizer of a subgroup. So we start with the product of subgroups. So this was the topic we were discussing in the last session, and we ended with this topic. So product of subgroups is defined like this. So suppose we have a group, say G, and H and K are two subgroups in G. Then product of H and K is the collection of elements of this form HK, like product of elements of H and K, keeping the order in mind. That is, first we will have elements from H and then from K, and we will uh, compute their product using the group operation. In the previous tutorial session, we discussed that the product of two subgroups need not be a subgroup. And we discussed an example for this. So what will be the criteria for product of two subgroups to be a subgroup again? So let H and G be two subgroups in G. Then HK, that is their product, is a subgroup of G again, if and only if HK is KH. That is, there is no restriction on the order of product of elements. Okay, if H and K commute with respect to the product of subgroups, then we say that HK will again form a subgroup of G. Now, how we calculate the order of product of two subgroups? So to compute this, first we need to consider that H and K are of finite orders. So if H and K are finite subgroups of G, then we can discuss about order of HK, that is order of their product. So order of HK will be this one. Order of H into order of K divided by order of H intersection K. So here, as H and K both are subgroups, so H intersection K will be a subgroup again. So that's why we can like discuss about their order. So using this, we can solve some questions based on order of H product G. Okay, come to this question. Let G be a finite cyclic group and H and K be two subgroups of G of order 12 and 10 respectively. Then find order of H intersection K and order of HK. Okay, so how to do it? First, what is given to us? That order of G is finite and G is cyclic. Okay, and H and K are subgroups of G such that order of H is 12 and order of K is 10. Okay. Now, as G is cyclic, then H and K will be cyclic subgroups of G. Okay, as all the subgroups of a cyclic group are again cyclic. Okay, so H and K are cyclic. Now, H and K are cyclic finite groups, and we know that every finite cyclic group is isomorphic to Zn if order of that subgroup is n. Okay, so here we can say that order of H is 12. So H is isomorphic to Z12 and order of K is 10. So K is isomorphic to Z10. This is actually like uh, Z over 12Z, and this is like Z over 10Z. Okay, so now since Zn has a unique element of order 2, if n is, okay, simply n is even, it will be greater than 1 then. Okay, so we can say that H and K will have a unique element of order 2. Say A belongs to G such that order of A is 2, and then A belongs to H and A belongs to K. Therefore, A belongs to H intersection K, or we can say that order of H intersection K is greater than or equal to 2. Because identity will be there always, and we get another element like other than identity, which is A, and that is an element of H intersection K. So its order can be either 2 or greater than 2. Okay, now H intersection K is a subgroup of H, and H intersection K is a subgroup of K. So order of H intersection K will divide order of H, and order of H intersection K divides order of K using Lagrange's theorem. Therefore, order of H intersection K will divide GCD of order of H and order of K. This implies that order of H intersection K will divide GCD of 12 and 10, that is 2. It means order of H intersection K can be either 2 and 1. But order of H intersection K is greater than or equal to 2. Therefore, order of H intersection K is 2. Now, we need to compute order of HK, and we have this result. So, we know that order of H product K is order of H, order of K divided by order of H intersection K. So this will be 12 into 10 divided by 2. So this will be 60. Okay. Now consider the second question. Let G be a group of order PQ, where P and Q both are prime numbers and P is less than Q. Then G has a unique subgroup of order Q. How to do this? Let order of G is PQ, where P is less than Q. So suppose on contrary, G has more than one subgroup of order 2. Say H and K of order Q. That is, order of H is 2 and order of K is, sorry, this is Q. Okay, then how to do it? What about H intersection K? So as the identity element will be in H and K both, so this will be in H intersection K. Therefore, H intersection K is non-empty. And it has if uh, there exists some A belongs to G such that A belongs to H intersection K and this A is other than identity, then what will be the problem? We are willing to claim that H intersection K must be trivial one, that is identity. So if there exists some A belongs to G such that A is in H intersection K, then this A will be in H and A will be in K, and obviously order of A will be this will be Q. Then the subgroup generated by A, this will be in H, and subgroup generated by A, this will be in K, but order of the subgroup generated by A, this will be Q. Now, um, if we have this order of HK, this will be order of H, order of K divided by order of H intersection K. So here if we have this order of H intersection K as 1, then what will be the problem? And why this is 1? Because, okay, so if we have order of the subgroup generated by A is Q, which is in H and K both, then H and K will be same. Okay, but we want to find two distinct subgroups H and K which have order Q. So that's why we need to stick with this assumption that there is no element other than identity in H intersection K. Therefore, H intersection K is identity, or order of H intersection K, this is 1. Now, order of H intersection K is 1. This gives us order of HK is order of H into order of K, and both are Q. So this will be Q square. But HK, this is a subgroup of G. Why this is a subgroup? Okay, because we are taking a group of order PQ, so that's why this can be either. Uh, okay, so till now we haven't discussed like what will be the form of group, and say like for a given natural number n, how many how many groups will be there up to isomorphisms, and what will be the form of that. So that's why, okay, fine. We will come to this in later section again, like what will be the form of group if its order is p by q, but still, if this hk, if this is subgroup of G, then order of HK, which is Q square, this is greater than PQ. Why? Because Q is greater than P. It means this is greater than order of G, which is not possible. It is a contradiction. Therefore, we can't have more than one subgroup of order Q. Okay. Now the next topic is center of a group. So center of a group is a set of all those elements of the group which commute with all other elements of the group. That is ZG. This is the notation for center of a group, G. So this is the collection of all X belongs to G such that XY is same as YX for all Y belongs to G. That is, ZG is the set of all X which commutes with all Y in G. We can prove that center is a normal subgroup of G. That is, it is a subgroup of G and it will be normal for any given group. And if G is abelian, then ZG is G. Okay, now come to this question. Which of the followings is are true? We have this 4 statements and there can be either one or more than one true statement. So we need to check all. So the first statement is, if G is a cyclic group, then it has a unique element of order 2. If G has a unique element of order 2, then it is cyclic. If G has a unique element of order 2, then the element commutes with every element of G, which is equivalent to say that the element an, uh, is an element of center of G. And the last one, if G has a unique element of order 2, then the order of G is even. Okay. Solution. Consider the first statement. If G is a cyclic group, then it has a unique element of order 2. Okay. So, two things. this is not mentioned whether this group is finite or infinite. So we can have both cases. Okay, and we can have a counter example for finite group also. So let G be a finite cyclic group of odd order. If G has some element of order 2, then uh, then we can construct a subgroup which is generated by this element of order 2. So first say this is A, that is order of A is 2 and A belongs to G. Then this is a subgroup of G and order of this is 2. Why? Because A will be there. Now we will consider its power. So whenever we'll take A square, that will be identity because the order is 2. Okay. So there will be no other element in the subgroup generated by A. But by Lagrange's theorem, we know that uh, if we have a finite group, then order of its any subgroup will divide order of G. Okay. It means order of this, order of the subgroup generated by A, this should divide order of G, or G is even. Okay. But we started with a group of odd order. So this is a contradiction. Therefore, G can have no element of order 2. Okay. Similarly, we can search some sort of examples in infinite cyclic group. But the statement is if G is a cyclic group, then it has a unique element of order 2. Okay, so this is not true. But what if we modify this? If we say like if G is a cyclic group and it has an element of order 2, then the element is unique. Okay, so basically the problem in the first statement was the existence. We cannot be sure about existence of such element. If existence is confirmed, then we can say like uniqueness will be there. Okay, now what is the reason behind this? If we have an element, if such element exists, then so if A belongs to G such that order of A is 2, then we know that A will be same as s- order of A will be same as order of XA X inverse. Okay, that is order of this will be 2. So this will give us the required result. because A same as X A X inverse or simply we can say this will be same as G is abelian. Okay. So G is cyclic, so G will be abelian. That means AX is XA. It means A and XA X inverse, they are same. So whenever we will have another element of order 2 of this form, that is XA X inverse, so that will be same as A. It means the element of order 2 will be unique. Now the second statement, if G has a unique element of order 2, then it is cyclic. It is cyclic means the group is cyclic. So is it true? Uh, we haven't discussed yet about quaternion groups. Okay, fine. So we can have a counter example for this. Mm, the quaternion group Q4, or sometimes this is denoted as Q8. So it has a unique element of order 2, but it is not cyclic. Okay. Can be similar if we say like if G has a unique element of order 2, then the group is abelian or not. So the same counter example will work for that. Third statement, if G has a unique element of order 2, then the element commutes with every element of G. Okay. So it A belongs to G such that order of A is 2 and A is unique. We can say there is no other element of order 2. We know that order of A and order of XA, X inverse, they are same. It means order of XA, X inverse, this is 2. And there is unique element. So these two forms or these two elements must be same. That is A is XA, X inverse for any X belongs to G. This will give us X, AX is XA. Okay, we can multiply by X from right, and then we can use associativity and identity in there. So we will have that. So this is true for all X belongs to G. Therefore, A is unique. It can be like it can be said as A belongs to ZG. That is the unique element of order 2 that will be part of the center of G. Okay. If G has a unique element of order 2, then the order of G is even. Okay. So A belongs to G such that order of A is 2. So again, we can consider this subgroup generated by A. Its order is 2. So by Lagrange's theorem, this will give us that order of G will be some uh, multiple of 2 or even. So yes, the statement is true. Now we come to the representation of a group. So we can discuss this in short. So if we have a group G, then it can be represented like this. So here, uh, G is generated by some element. So this capital S represents here the generators of the group G or the elements of the group G which are sufficient to find all the elements of G. Okay, and this capital R is some relation between the generators. Like we can have an example S3, which is a permutation group. So it can have two generators, or like I should write it as either I should write it like this or like sigma I tau j, where I and j are 0 to y because sigma square is identity and tau square is identity. Okay. So for S3, we will have two generators and sigma square. Uh, See, if the generators are sigma and tau, then both will be of order 2. So this is the first relation. And the second one is that sigma tau, the product will have order 3. Okay. So for example, we can have sigma as this permutation and tau as this permutation. So this will generate S3. Similarly, we can represent the dihedral group, which is symmetries of regular polygons. So suppose we have Dn. Note that here I'm representing n. mm, like I'm using n to represent the degree and order is 2n. Okay, so Dn, this is generated by x and y. It will have two generators. One will be the reflection, second one will be the rotation, like as we discussed in the previous session. So from these two generators, x and y, x will have order 2 in Dn and y will have order n. Like order of y will be the degree of the dihedral group. Okay, and we will have this relation. Xy is y inverse x, which is equivalent to like this. Xy is y inverse x inverse, but x inverse is of order 2, so that's why x inverse and x they are same. Okay, so these two are equivalent. Okay, now we have another group, Kleins 4 group. So this is a group of order 4, which is generated by two elements, A and B. So note that here I am using two elements to generate this. K4 cannot be generated by a single element. So this is a non-cyclic group and it has four generators, identity 1, A, B, and AB. Okay. So A square is identity, B square is identity. It means uh, both have order 2, and AB is BA. It means the group is abelian. Okay, so that's why we cannot have more than these four elements in K4. Whenever we will have A square, we will get the identity. Whenever we will have B square, we will get the identity. Whenever we will multiply A or B by E, we will get the element A and B again. And what about AB or BA? They are same and the element will be other than E, A and B. Okay, so K4 has exactly these four elements. And this is an abelian group and this is non-cyclic. Okay, so we can also say that this is isomorphic to Z over 2Z, Z over 2Z. Okay, these two are isomorphic. Now the next one is quaternion group. Mm, This is the counter example which I have given for some previous question. So this group has three generators, I, J and K, and I square, J square and K square. They are minus 1. Okay, not 1. It means I4, J4 and K4, they are 1. That is I, J and K, they have order 4 in Q4. Okay. In this one, I, J, K is minus 1. That can be, it can be reduced in I, J is K, or this is minus Ji. So from this, we can see that the quaternion group is non-abelian. If I want to list all the elements, then we will have 1, which is the identity. We will have minus 1. Okay, so 1, this can be obtained by I 4, or like J4 or K4. Minus 1, this is like square of IJ or K. Then I, J, K, minus I, minus J, and minus K. So if I like to mention orders, so 1 has order 1, minus 1 has order 2. Was like minus 1 square, we will have that 2. I, it will have order 4, J and K, 4. Why? Because like I square is minus 1, so that's why. Similarly, minus I, minus J and minus K, they have orders 4. It means it has a unique element of order 2, a unique element of order 1, which is obvious, the identity element, and it has 6 elements of order 4. Now, we have the definition of center, and we know that it is a subgroup, mm, normal as well. So let's come to some computational examples. We have these three groups and we need to find out their centers. So first, what about Q4? So center is denoted by ZQ4. Okay. So as we know by the identity axiom, actually, AE, this will be EA for all A belongs to some group. Okay. So identity will always be a part of center. So what is the identity of Q4? We denote that by 1. So 1 will be here. Then C. IJ, this is minus JI. It means I and J cannot be a part of center. Uh, Similarly, we can have this JK is minus KJ, means IJK, as well as minus I, minus J, minus K. They can't be a part of center. But what about this minus 1? This commutes with every element. So this is a part of center of this. Okay. Secondly, GLNF, where F is some field. So what is GLNF? This is group of all n by n non-singular, that is determinant other than 0, matrices over F, which is some field. Okay. So if F is infinite field, that is Q, R, or C, then so we need to find the center of GLN-F. That is, we need to find all those matrices which commutes with every metric, any given matrix. Okay, means center of GLN-F. This is group of matrices that commute with every n by n non-singular matrix. And we know by linear algebra that scalar matrices will have such property. Okay, that is, scalar matrices commute with uh, every matrix of same order. Okay, so this will be that I can write it in this form. Such that A belongs to F star. See, like A equals to 0 will commute, but actually that is not a part of GLN F itself. So that's why. Okay. Or this can be written as like this also, AIN, where A belongs to F star. Okay. So if F is infinite field, then center of GLN F will be infinite. Okay. Why? Because this Q star or R star, C star, all are infinite. Okay. So this will be the form of center. And order of Z, GLN F, this is infinity if F is infinite. Okay. If F is finite, then again order of Z, GLN F, this will be order of F star. Okay. So if we have FQ, then order of FQ star, this will be Q minus 1. It means if we have a finite field, then we will have Q minus 1 central elements of the group GLNF. Okay. Now the third one is center of special linear group, SLNF, and if we restrict F with R. Okay. So what is SLNF? This is the set of all matrices A of order n by n such that determinant of A is 1. Okay. And center will be, so again, for a matrix to be a central element of SL and F, it must commute with every n by n non-singular matrix. So obviously only scalar matrices will qualify the restriction. And we have another condition like center of this. So this will be a group of all, okay, let's leave it. The group of all those matrices such that uh, A is AI or some A belongs to F such that determinant of A must be 1. Okay. And we know that determinant of AB, this is determinant of A, determinant of B. So this implies that determinant of A, if A is in ZL and Z, SL and F, so this will be determinant of AI, which is AN. And this must be 1 if A belongs to Z, SL and F. Okay. Let A belongs to this. So now it is remaining to check this. AN is 1, that is okay, so let's split the case in finite and infinite field. So if we have a finite field, or simply write if F is a finite field, then A, okay, AN is 1. Mm, This implies that order of A divides N. Okay. So we can have all those numbers from the finite field whose order divides mm, the number n here. Okay. It means we will collect all the positive divisors of given n, and then we collect the scalar matrices with respect to those elements. Okay. That collection will form the center of SL and F if F is a finite field. Okay. That is Z, S, L, and F. This is collection of AI such that order of A divides N in F. Okay. It means we need to find the number of positive divisors of n if we want to find the order of center of this special linear group. Okay, so Euler's phi function will work for us. Now, what if f is infinite? For example, r, then again we have this condition, an must be 1. Okay, so an can be 1 if a is 1 and n is odd, and if n is even, then it can be 1 and -1 as well. Okay, it means in this case center will be this is either identity element and negative of that, or only the identity element, which depend what is the value of n. So this is for even n, this is for odd n. Okay, but this is for R. This can work for rational field as well, but not for C. What if the finite field is C? So there we need to uh, reconsider this condition. An is 1. It means A is nth root of unity. Okay, so we will have n values of A there. It means the center will be isomorphic to Zn in this case. Isomorphic to Zn. Okay, with respect to nth root of unities. Okay. Now, quotient group, which is Q over Z. So this is discussed in lecture videos in detail. So I'm just giving a quick summary of this. So Q over Z is the group of elements of the form P over Q plus Z, where if we consider P belongs to Z and Q belongs to N, then GCD of absolute value of P and Q, that is 1, whenever P is non-zero. Okay, so this is an interesting example of group because it has all elements of finite order. You can refer the lecture videos to know more about what will be the order for a given element. Okay, so this is example of a group in which all elements are of finite order, but the group itself is infinite. Okay. Now, hmm, we can see that these two groups, we can have a homomorphism between them, GLN R and R star, and we define it by determinant, that is the map. So whenever we will have an element of GLN R, which are matrices, and if we map it, or if we want to correspond this with an element in R star, then what we can do, we can find the determinant of it, because determinant is um a real number actually. And in GLNR, we are taking non-singular matrices. That's why determinant cannot be 0, and this assures that we will not go to R. Okay, and yeah, so this is a multiplicative group, both actually. So in GLNR, we use multiplication of matrices, and in R star, we use multiplication of real numbers. That is the usual multiplication we do. Okay, so what is the kernel of this isomorphism? The kernel will be the group of all those non-singular matrices of order n by n over R, which has determinant 1. Okay, and yep, this is a normal subgroup of GLNR. Again, uh, we have another homomorphism for this GLNR, and for that we use the permutation group, that is SN. So this is the group of all permutation from IN to IN. IN is like the set 1, 2, 3 up to n. So this sigma is a bijection. And we have an injective homomorphism from Sn into GLNR. If we denote it by iota, so what will be the form of this? This iota of some element sigma, this will be given as this sigma of I n by n. Okay, so actually in GLNR, we have matrices. So for this, we consider the identity matrix, or should I write all as 0? Mm, okay. Okay. So we consider the columns of the identity matrix of order n. Okay. And with the help of these, we define the homomorphism iota. Okay. So iota of sigma is sigma of in, which is represented as I sigma. What is I sigma? I sigma is redefined as this form. Like I sigma is defined by mentioning the columns of this matrix, and these columns are redefined. Okay, so now the first column will not be 1 0 0 0 always. This will be the column with respect to sigma 1. Okay, so if here we have 1 2 up to n, and this will be sigma 1 sigma 2 sigma n. Okay, so from here we will have sigma 1 sigma 2 and so on. So suppose we have this sigma 1. Okay, so the first column of I sigma will be E sigma 1. So if sigma 1 is 5, so first column of I sigma will be the fifth column of identity matrix. Okay, so in this way we define I sigma, and image of sigma under I, this is I sigma. Okay, so this is an injective homomorphism from Sn into GLNR. Using these two maps, we define the signature of some permutation. Okay, in short, sign. So sign of some permutation sigma, this is determinant of I sigma. Okay, so note that I sigma here, mm, these are actually the collection of n by n matrices whose columns are actually formed using reshuffling of columns of the identity matrix. Okay, so whenever we will find the determinant of I sigma, uh, there there are two possibilities, either 1 or -1. Okay, so sign is Actually, this is again a map which is the composition of these two maps, determinant and I. So determinant is from GLN R to R star, and iota is from SN to GLN R. So in this way, signature is a map from SN to R star, okay? But only two real numbers from R star are permitted here, -1 and 1, okay? Uh, Now what is sign of a permutation? It can be either 1 and -1. And how to find it? By calculating the determinant, or simply we can say like how many times we are switching two columns of the original identity matrix. Okay, so each reshuffling, each switching of two columns from their initial position, that will contribute -1 in the determinant. Okay, so in this way the sign will be -1 into number of such reshufflings. Okay, so obviously that can be either +1 or -1. So in this way, we can find a signature of a given permutation from Sn. And if signature is +1, then we say that the permutation is even permutation. If the signature is -1, then we say that the permutation is odd permutation. Okay. So we have two types of permutations, odd permutations and even permutations. And the collection of all odd permutations, that is the collection of all those permutations which have a signature 1, forms a group of Sn, and this group is known as the alternating group. Okay, so this is actually the kernel of the signature map. Why? Because obviously the kernel will be defined as the image will be the identity element of R star. And what is the identity element there? That is 1. So if we collect all those sigmas which have signature 1, then we will get the kernel of the signature map. And we know that if we can have such homomorphism, then the kernel will be a normal group, okay, in the domain group actually. So in this way, we can say that AN is a normal subgroup in SN. It means alternating groups are always normal in symmetric groups. And what are alternating groups? They are collection of all odd permutations. And we have another result actually. What is order of Sn? This is factorial n. Why? Because any element of Sn, so this can be formed, sorry, this will be n. Mm, this can be formed by shuffling the images between 1 and n. Okay, so the sigma 1 and then sigma 2. So here we can have n choices, and here we can have n-1 choices as we have to reduce the image of 1 from the set of possibilities. Okay, and at last we will have single choice. So order of Sn, that is factorial n, and Sn is the set, is a group of all permutations, and every symmetric group has equal number of even permutations and odd permutations. And we have this, that order of An, this is a factorial n by 2. So now what are direct products of groups? So we can have two types of direct products actually, external and internal. The internal one can be defined using the concept behind external direct product of two groups. So if we have two groups with their associated binary operations, say G1 and G2, then the direct product of G1 and G2, that is G1 cross G2, this is the set of all elements of the form this x comma y. Here x is coming from G1, Y is coming from G2. And the group operation is redefined here. Okay, this is the operation of G1 cross G2. Okay, and this is defined like this. So here we are using the operation of G1 and here we are using the operation of G2. Okay, so with the help of group operations of G1 and G2, we get another group operation for the group G1 cross G2. So this group G1 cross G2 is something different from the type of the group G1 and G2. Okay, and this is how we can have the identity element and how we define inverse. So obviously identity element, it means the point-wise identity, and the inverse again we calculate point-wise, or like group-wise we can say, which are being used to define the product. Okay, so here G1 cross G2 is some another group. Okay, this is why we say this is external direct product. Now, what is internal direct product? So, internal direct product, we define this for subgroups. Okay, not for group, because we need to fix the operation. Okay, that's why we start with a group and we consider two subgroups in this, say H and K. Then G is called a direct product of H and K. Note that we have already discussed what is product of H and K. Okay, so HK, this is product of two subgroups H and K. But if we say this is a direct product, then what is the additional property here? Okay, so G is called a direct product of H and K, which is denoted like this. G is isomorphic to H cross K. If H and K must be normal in G, first thing. Second thing, the product of H and K, that is HK, this must be G, and H and K, they are disjoint. Okay. Uh, okay, in set theory actually, disjoint mean they don't have any common element. But in group theory, disjoint group means those group which have only the identity element in common. Okay, disjoint subgroups actually. So it says that whenever we have an elements, an element G belongs to G, there exist unique elements. H belongs to H and K belongs to K, such that G is HK. The way we are defining product for capital H, capital K, the product one. Okay, if G is a group and H and K are its subgroup, then followings are equivalent. So these are the necessary and sufficient criteria for H and K to be like to generate the direct product of G. Okay. This is an example. Say this group Z over 6Z. So here 6 can be written as 2 into 3 and they have GCD 1. So we can write Z over 6Z as direct product of Z over 2Z and Z over 3Z. Okay, so these are some another results on normal subgroups. So wait, hmm. So what is the normal subgroup actually? So say G is a group and H is a subgroup of G. Then we say that H is normal, which is denoted by this. Let me rewrite it. If G, H, G inverse, this is same as H for all G belongs to G. Okay, so this is the definition, or I can say this is one of the definitions of normal subgroups of a given group. So these are some another equivalent conditions for a subgroup to be normal. In the previous problem solving session, um, some students asked for examples of normal subgroups, or like what are the key results, or like what is the technique to determine whether a given subgroup is normal or not and the underlying group. So let's discuss that. So first we have an example where a subgroup is not normal. Okay, so suppose we have this. The group is S3. That is the group of all symmetries of equilateral triangle. Okay, so it has 6 elements, note that. And if we consider this subgroup of S3, which is identity and the element 1, 3, that is which map 1 to 3, 3 to 1, and 2 to 2 itself. Okay, so this subgroup is not normal in S3. Why? Like we can have this element in S3, okay, and then we can say G, H, G inverse. So in this we can have another element 2, 3, which is not in H. So that's why we can say that this is not normal in S3. It is a subgroup, but it is not normal. Um, okay, so if we have a finite group, say G, and H is a subgroup of G, and we have this notation says the index of H in G, that is the number of distinct left or right cosets of H in G. So if that is 2, or equivalently we can say if order of G by order of H, both we can define as G is finite. So if order of G by order of H is 2, then H is normal in G. This is a very useful result actually. And by this result, actually we can say AN is a normal subgroup of Sn for a given n. Why? Because order of AN is factorial n by 2 and order of Sn is factorial n. So that's why AN has index 2 in Sn. So alternating groups are normal. Okay. We can have a generalized version of this result. So for a finite group G and a subgroup H of it, if index of H in G is P is a prime number, and if P is the smallest prime number which divides order of G, okay, then then H will be normal in G. Okay, so actually this can be true for a group of even orders. So obviously if a group is of even order, then like we can have a group of index too. So like this can be this be a particular case of the second one. And we know that intersection of all subgroups, or intersection of any arbitrary collection of subgroups of a given group is again a subgroups. So the same holds for normal subgroups. That is, for any collection of normal subgroups of a given group, the intersection will again be normal in G. now what is normal subgroup generated by a subset? So this can be defined in the same way we define what is a subgroup generated by a given subset. So a subgroup generated by a subset is actually the intersection of all those subgroups which includes the given subset. Okay, it means this is the smallest subgroup which contains the given subset. Okay, but if in place of just subgroup we use normal subgroups, and if we consider the intersection of all those normal subgroups which contains the given subset, then we get normal subgroup generated by the given subset. Okay, what is a simple group? So a simple group is a group which has only two normal subgroups, that is the trivial one, identity, and the group itself. Some examples of simple groups. So Z over NZ. This will be simple if and only if P is a prime. Why? Because if this is prime, say P, then we will have this Z over NZ, or say Z over PZ, and this P will have only two divisors, 1 and P itself. So and this is a hint. We can say that we cannot have more than two normal subgroups, or actually more than two subgroups cannot be possible there. And alternating groups. Okay. So if n is greater than or equal to 5, then we say that Sn are simple, because An is the only okay, in that case An is simple. Okay, because An is the only normal subgroup of Sn. Come to this question. If all subgroups of a group are normal, then is the group cyclic or not? Can we have a counter example for this? So consider this group, say G is Q4, that is the quaternion group. And okay, this is plus minus 1, plus minus I, plus minus J, and plus minus K. So what are the subgroups in this? Subgroups of Q4. So first, the identity one. Okay. So as we know, identity is always normal in given group. So yes, this is normal. And I should write this. Okay. Secondly, 1 and minus 1. Because minus 1 is an element of order 2. Okay. So this is a subgroup generated by minus 1. It means minus 1 and like powers of that. So minus 1 to the power 1 means minus 1, and its square will give us 1 again. So and this is a subgroup of order 2. Third, mm, what if we take this, the subgroup generated by I? So this will be I square, I cube, I4, and so on, if possible. So this is I square is minus 1, I cube minus 1, I means minus I4, this gives us 1. Okay, so yep, there are exactly these 4 elements. So this has 1, minus 1, I, and minus I. Or we can say this is generated by minus I as well. Similarly, we can have a subgroup generated by J or minus J. This is plus minus 1 plus minus J. I'm writing this for simplicity actually. Mhm. Then subgroup generated by K or minus K. Any other? Actually, if we use Lagrange's theorem, we know that order of H divides order of G if order of G is finite. So, yep, if G is Q4, then order of G is finite, which is 8. So, order of any subgroup of it will divide H. Okay. So, possible orders of subgroups of Q4 can be 1, 2, 4, and 8. That is all positive divisors of 8, order of group. Okay, so subgroup of order 1, that will be unique, the trivial one. Subgroup of order 2, so that is the subgroup generated by minus 1. It has a unique element of order 2, so it cannot have more than one element of, more than one subgroup of order 2. Now subgroups of order 4. So we have these 3. Can we have another possibility? So, no. Why? Because other than 1, we need to include like something from I, J, or K. So, if we include I, so this will generate this. And whenever we try to include I and J, then note that their multiplication will give us K. Okay. So, the last possibility can be Q4 itself. Okay, means it will include all the elements. That is, Q4 has one subgroup of order 1, one subgroup of order 2, three subgroups of order 4, and one subgroup which is obvious of order 8. Okay. Now, which one is normal, which one is not? So, order 1, so this will be normal and this will be normal because E and G are always normal subgroups of a group G. Okay, so these two will be normal. Now, what about uh, remaining? So, for this, subgroups of order 4. So, for this, we can consider this result. If index of H in G is 2, then H is normal in G. So, yeah, the subgroup generated by I, J, or K have indices 2 in Q4. That's why all these are normal. Now, what about the subgroup generated by -1? So, actually, it is a unique subgroup of order 2. So, this will be normal. But again, if we want to calculate this, we can have some explanation for this. This is normal if G H G inverse, this belongs to -1, where uh, or I can say for all G belongs to Q4 and H belongs to this -1. So H can be 1 or -1. So this is true if H is 1. Okay. So if H is 1, so this will be G inverse, which is the identity element. Okay. So which is in the subgroup generated by -1. What if H is -1? Then G -1 G inverse. So yeah, this will be -1. Okay, which is in the subgroup generated by -1. So that's how we can conclude that -1 is normal. Okay, so these are the 6 possible subgroups of Q8, and all are normal, but the group is not cyclic. Okay. All subgroups of Q4 are normal in Q4, but Q4 is not cyclic. Okay. So the statement is false. Note that Q4 is non-abelian as well. Okay. For example, ing, they don't commute. So we can have an alternate statement, or this example can work as a counter example for the statement. If I say, like, if all subgroups of a given group are normal, then the group is abelian. Okay, so yep, that statement will be false. So I'm writing it in general way. If all subgroups of a group are normal, then G is, or you can say G need not be abelian. Okay. Uh, okay. Actually, this is the statement I wanted to write. Okay. So the statement is false. And what can be a counter example? Q4. Mm, okay. Actually, like if we want to construct some simpler example, some easy example for, I would like to avoid the term simple or normal here, mm, as they have some specific meaning. So if you want to compute some easy example for this, like other than Q4, can we have a counter example? So, yep, simply we can use this. If G is Z over 2Z cross Z over 2Z, or we can use K4. So, as G is abelian, all subgroups are normal, but G is not cyclic. Okay. But this counter example will not work for this. Why? Because here all subgroups are normal. G is non-cyclic, but G is abelian. So if we want to find some group having all normal subgroups, which is non-abelian, then we can go to this counter example Q4. Okay. Consider this statement. If all proper subgroups of G are cyclic, then G is cyclic or G is abelian. So, is this true or not? Note that here I am saying all proper subgroups, not all subgroups. Okay. Because whenever we will have all subgroups of G, then obviously G is itself a subgroup of G. So if we say all subgroups of G are cyclic, so this implies that G is cyclic. So there is no sense to formulate the statement actually. Okay, so this is why we are using here proper subgroup. So the statement is if all proper subgroups of G are cyclic, then is G cyclic or is G abelian? So again, we can use this example Q4. Okay, we see that it has these 6 subgroups, out of which uh, first 5 are proper and they all are cyclic. Okay, this is generated by 1. Okay, so since Q4 has all uh, Q4 has 5 proper subgroup? Namely, generated by 1, subgroup generated by -1, I or -I, both are same. Subgroup generated by J and subgroup generated by K. And all are cyclic, but Q4 is non-cyclic. Therefore, statement is false. Okay. Now, again, uh, we want to have some more examples on normal subgroups. So first we recall some useful results on normal subgroups. So if H is a subgroup of G, then this will be normal if either of these three conditions are true. That is, if GH G inverse is an element of H again, or if G capital H G inverse is capital H, or this GH is HG, that is the left and right coset of H with respect to the same element G are same, and this is true for all elements G belongs to G, then we say that H is a normal subgroup. Secondly, if we have a cyclic group or if we have an abelian group, then we can say all subgroups will be normal. Okay. Third one is if the subgroup is a part of center of the group. Okay. Or we can say if H is a subgroup of center of a group, then the subgroup will be normal. Fourth, if H is a unique subgroup of order 2, then it will be normal. Next, if the index of H in G is 2, then H is normal. And another one, if index of H in G is P, where P is the smallest prime which divides order of G, then H is normal. We have that also. And if H is a subset of K and K is a subset of G and H is normal in G, then H is normal in K also. Okay. So we can use this results or definitions to find normal subgroups of a given group, or to check whether a given subgroup of a group is normal or not. So let's do some questions. First one, if order of G is 4 and x square is identity for all x belongs to G, then find the number of normal subgroups of G. Since order of G is 4, then G can have elements of order either 1, 2 or 4. Uh, this is the conclusion we obtain using only the first assumption that order of group is 4. Okay, because order of element divides order of G. So other than 1, 2 and 4, we cannot have any possibility for order of elements of G. Okay. But x square is identity for all x belongs to G. This implies that order of x divides 2 for all x belongs to G. That is, order of X can be 1 or 2. Obviously, for 1 we will have identity element, and for 2 we have remaining 3 elements. Okay. It means we have a group of order 4 which has identity and 3 elements of order 2. So the group can be isomorphic to either we use this notation or we can write K4 also. Okay. So we want to find number of normal subgroups of G. So first of all, what are the subgroups of G? Okay. I'm writing it as E, A, B, and AB. Perfect. So first subgroup is identity one. Secondly, the subgroup generated by A, that is identity and A. Now we have two more elements of order 2, that is B, which is identity and B, and lastly generated by AB, which is identity and AB. Okay. Now, if I want to include A and B both, then we will have a product of that, and obviously identity will be there if we have A into A, that is A square. So this will give us the entire group G. So we have this 4 subgroups of G. Okay. Now, which is normal, which one is not? So this is normal and this is normal, because these two possibilities of subgroups, identity one and the group itself, are always normal. Okay. Now, what about this one? So the subgroup, actually the group is abelian. Okay. Like if we want to check, we can, otherwise we can just give this uh, and logic behind this. The group G is abelian, therefore all subgroups are normal, or G has how many? Five. Five normal subgroups. Mm, Okay. The help of this example, I would like to clear that if we have a unique subgroup of order 2, that will be normal. But if we have a normal subgroup of order 2, that should not be unique in general. Okay, I'm writing it. Unique subgroup. But if G has a normal subgroup of order 2, the subgroup need not be unique. Okay. Now come to this. What is the group G? G is D6 cross Q4. That is the direct product of D6 and Q4. Okay. It means it will have elements of the form X, Y, where X belongs to D6. That is like the first element of this tuple XY will be some symmetry. Okay, like either this will be some reflection or rotation. And the second one will be some quaternion number. Okay, that is plus minus 1 or plus minus I plus minus j plus minus k. Okay. And H is this subgroup generated by R180 minus 1. What does R180 mean? It means the symmetry of the given regular polygon uh, obtained by rotating the polygon by 180-degree anti-clockwise. So, okay, let's this is D6 fate. R180 means 360. Okay, fine. So I'm writing D4. So then 160 will be half of 360. Okay, so this will give you exactly a central element. Okay, so here as well. Since R180 belongs to center of D4, why? Because exactly there is like the sum of all angles of regular polygon here, which are squares actually. So that is 360. Half of that is 180. So whenever we will rotate by this, this will be a central element. Okay, for that we can consider this question also. What will be the center of Dn? Okay. So try to do that. If you have some difficulty, we can discuss in next tutorial session if you say. Okay. And minus 1 is a part of center of Q4. Therefore, this H will be a subgroup of the center of E4 cross Q4. Therefore, H is a normal subgroup of G. Okay. like how to find center of G1 cross G2. So for that, we need to consider center of G1 and then center of G2 and the direct product of that. That will be the center of the direct product, the product G1 cross G2. Okay, not that direct product, the external product, I can say. Okay, so yeah, this is a normal subgroup. Why? Because this is a subgroup of the center of the given group. Okay, and we discussed that a part of center is normal. What about this? Is H, which is given by this, is normal in GL3F7. GL3F7 means 3 by 3 non-singular matrices where elements or like entries are coming from the finite field F7. Okay. So yes, H is a normal subgroup of GL3F7. What will be the center of GL3F7? We have already discussed it, and H is a part of this. Okay, so this is how we can conclude that H is normal. Now find normal subgroups of Q4. So we have already discussed it. This is quaternion group, and it will have all proper subgroups normal in Q4. Okay, that is subgroup generated by 1, -1, I, J, and K. Okay, and Q4 itself, as it was not asked that we need to find only proper normal subgroups. Okay, now show that this is a normal subgroup in the given group. So here the group is GLNR, that is n by n non-singular real matrices. And what is H? This is a set of all those matrices in GLNR such that it has a positive determinant. Okay. So first we need to check that H is a subgroup of G. Okay. So since the identity element has determinant 1, here I'm denoting it by this, no problem, you can use either notation. This is 1 which is positive. By this I mean positive actually. Okay. Therefore, identity belongs to H, or H is non-empty. Okay. Now let A1 and A2 belongs to H such that a determinant of A1 and determinant, okay, this belongs to H. Therefore, determinant of A1 and determinant of A2 are positive. Okay. What we need to conclude that A1, A2 inverse, this is in H. So this will be in H if its determinant will be positive. Okay. So that's why we consider determinant of A1, A2 inverse. Okay. So again, we can use the properties of linear algebra. This will be splitted in determinant of A and determinant of A1, determinant of A2 inverse. So yeah, we can say this will be positive again. Therefore, A1, A2 inverse belongs to H, or H is a subgroup of G. It is GLN R actually. Okay. So now what we need to prove that H is normal. So here we use the definition. Let A belongs to H and should I use some, say B belongs to GLN R, then what will be the determinant of B, A, B inverse? Hmm? So this will be determinant of B, determinant of A, determinant of B inverse. Okay. And determinant of a matrix and its inverse have same sign. Okay. Therefore, determinant of B inverse, this will be positive because either both the determinants will be positive or negative. So that's why. And determinants are real numbers. So like real numbers are commutative. So that's why I'm writing it. So this implies that B inverse belongs to H because it has positive determinant. Therefore, H is normal subgroup of GLN R. Okay. So we have discussed a sufficient number of questions for mm, normal subgroups. So if you want more examples on this, or if you get difficulty in any a result or any criteria, then you can ask in upcoming sessions also. So now we have our last two concepts. We can discuss them in next session in detail. Normalizer and centralizer. So what is normalizer of a group? So for this, we need a group, say G, and a subgroup of it, say H of G. Then normalizer of H in G, this will be the collection of G belongs to G such that G, H, G inverse is H. That is, the normalizer is the largest subgroup of G in which H is normal. Okay. So actually, whenever we will have a group and a subgroup which is already normal in the group, then the normalizer will be G itself. But if we have a subgroup which is not normal, that is, if we have some H which is not normal in G, then can we have a part or can we have a subgroup of G in which H is normal? So yes, we can have, and the largest such subgroup uh, is known as the normalizer. That is a subgroup which normalizes a given subgroup of G. Okay. Here we are here we are saying the largest subgroup. And why normalizer always well defined? Because H is a subgroup of H itself, and H will be normal in H, obviously. So that's why like the smallest such subgroup in which H is normal is H itself. And this is why normalizer is well defined. But if we figure out what is the largest, then we can say that that is the normalizer of the given subgroup. Okay. Now, about a centralizer. So if we have a group G and a subgroup say H, then centralizer, which is denoted by this CG of H, this is the collection of all elements G belongs to G such that Gx is Xg. That is, centralizer is a collection of all those elements of G which commutes with every element of H. Okay. So centralizer, this is somehow related to the center of a group, and normalizer is related to normal of a group, like normal subgroups. Okay. So yeah, there are some questions, but I would like to stop today's session here only. We will discuss the remaining like the remaining problems on normalizer and centralizer and your doubts in next session. So that's all for today. Thank you.